Hello, everyone. Hope you're doing well. We've been learning a lot about this new toy that we've been able to play with, this notion of a metric space. Hopefully, over the last few questions that you have been working on through your exercises, you've gotten a little bit of a good notion of following things, examples of things that are metric spaces, as well as how to show convergence in a metric space, or how to show functions between two metric spaces are continuous. We've also gotten a few other tools underneath our belt that we're going to be using later on, namely the notion of little LP spaces and knowing that for any value of P, these things are able to be metric spaces, as well as equivalent metrics. Having the same space, but metrics in which not only are convergent sequences the same, but Cauchy sequences are identified as well. I want us to, before we move on to doing anything with metric spaces that are useful for us in this kind of modern era of analysis, namely looking at the world of Fourier series and differential equations, which we'll get to do at the end of this week, I want us to take a little bit more time with visualizing metric spaces. I want us to have a little bit more intuition, a little bit more of things to work toward, because metric spaces notably have much less structure on them than the real numbers do. You essentially just left with a space x with the structure of a distance in its most abstract form. Gratefully, we do have some examples of when you can subtract and when you can add things. We've talked about subtracting and adding sequences whenever you're looking at little L2 spaces, for example. This sort of process is kind of streamlined a little bit when you get some very nice things to help us out there. We'll see that these are examples of a particular type of vector space in our latter half of the course. But metric spaces are all that we need for much of the material that we need for working in this kind of world. So we're going to talk a little bit more about metric spaces at this level of abstractness, knowing that it's not necessarily true when I'm just given let X be a metric space, that I can add two terms or that I can subtract two things, that I can check if one thing is less than another. But what I am able to do is get a finite distance between the two of those values that satisfies a triangle inequality. So let's get a little bit more notion about how just this function alone is able to tell us so much about a space, because we can now start characterizing things called open and closed sets on those spaces. You may be familiar from this notion on topology in a way that's a bit more general. And typically, you can define a topology on a space X. You can do it in the following way. A topology T is a subset of the power set of that space that satisfies the following properties. First, you've got to be able to say that the empty set and the entire space are inside of this subset of the power set, or I should say this is a element of the power set, not a subset of the power set. So the empty set and X should be inside of this topology. The second thing is that if you have a collection of elements, let's call them U sub alpha, that is subset of this topology, then that's going to imply that the union over alpha of these U sub alpha is an element of this topology. That means that this is closed under a union of any size collection. This could be a finite collection. This could be an infinite collection of any size. This is saying that you can always take a union over any number of elements inside of that collection. And finally, the third condition is that if you have U1 through UN as all being elements of this topology, so a finite collection here, then we need to say that that's going to imply that the intersection, as I goes from 1 to n, of those sets are also inside of the topology. Notice that what we're doing here is doing something that we're eventually going to characterize as the open sets of a space X. The open sets of a set have these properties, namely that the empty set and the entire space are going to be what we call open. Now, if you've taken my Math 632 course or taken a Math 689 Intro to Grad Level course here, then you probably have remembered looking at open and closed sets when you were looking at interior and boundary and exterior points in the real numbers. And you can notice that all of these properties are true. That namely, the empty set and the set are open sets in terms of that. Every point inside of this is an interior point. You could also check to see that the arbitrary union of open sets is itself open in the real numbers, as well as the finite intersection of any open sets is also open. So this is us defining what sets we're calling open in terms of a topology. The way that we start defining this for metric spaces is that we say, okay, well, we're going to define openness in terms of a metric. And it's all going to be in terms of the balls that we were talking about before. We're going to say that any union of things of this form, let's say you have a center of X sub alpha and E sub alpha, and that you union this over, well, any collection of the alpha there, then this is what we're going to be defining as the open sets. The open sets here are going to be the collection, the unions of any collection of balls of any particular points in the space center at any point, together with any radius for any point. So pictorially, we're looking at pictures like this, taking open sets like around in this world and saying you can union all of these together. They could even be touching one another, something like this. The union of all sets at this point of any size collection are going to be what we call the open sets. We can see, for example, how maybe you could get these two elements, the empty set and the entire set X, in balls of this form, maybe by just taking some point and continuing to expand the radius of how many points, because for any one given point, the distance from that point to any other arbitrary point is finite. So unioning over, say, for example, the space of all, if you take just some arbitrary point, let's say bx, inside of this space, and you consider the union of this as n goes from 1 to infinity, then you should see that this gets you the entire metric space that you're looking at, this being x being any element inside of the space. So you can see how you can get x in there. The empty set is the empty union. You're unioning no sense at all. Then arbitrary unions, you can see how these things can be open. And then finally, finite intersections is a little bit trickier, but we'll talk a little bit about how this sort of stuff can be found once we talk a little bit more about open and closed sets. But defining these to be the open sets of a metric space ends up being very useful for us. And we're going to talk about how this works in terms of the interior points of a set. So let's do that real quick. The interior points of a set are going to be all of those for which there is some sort of open ball around that point, such that that open ball is contained entirely within the set. So X is inside of this open ball, and that is contained entirely within this set. We want to do something similar too in talking about what are called closed sets. Notice how openness is going to be this value of taking all of these balls of radius x e epsilon, and how we've been defining it is the set of all. I suppose we've been here. I have calling x naught, so I'll go ahead and call this x naught epsilon and say that this is all the set x and x, such that the distance from x to x naught is strictly less than epsilon. But we're going to do a similar thing of something called a closed ball, which is going to be something that contains kind of like the sphere that you might say is the separation between the open ball on the inside and the outer space. So it's going to contain the place where the distance between x and x naught is equal to epsilon. So picture-wise, you can think we have, instead of it just being the open ball like this one over here, this being our open ball, notice that this is all the stuff on the inside and not the this kind of little separation spot. But a closed ball, on the other hand, would be all of the things on the inside, including that boundary. So looking at this in terms of R2, this gives us this little bit of picture. We'll get to closed balls in just a little bit, because closed balls do not have this property, which is for open balls, you could say, take a look at all of the interior points of that set. Every point of an open ball should be an interior point. We're actually going to go through and prove that on a later slide. So you can see here, that's exactly what we're doing in terms of the real numbers. What points in an open interval are interior points? All of them. If we pick any x inside of the open interval from a to b, we can pick the smaller of the values x minus a and b minus x and call that epsilon. We note that that value cannot be 0 since a and b are not inside of the open interval from a to b. So this subset, which is the epsilon ball around x, satisfies the property that we were looking for. Namely, this is the ball of radius epsilon around x, and that this is entirely within the set AB. Since x here was arbitrary, this is an interior point, and every point is going to be an interior point here for the real numbers. And so that kind of helps us characterize this definition in terms of how this looks in terms of the real numbers. This is exactly what I give my undergraduate students when we're going through topology. We say any point X and E is an interior point if you can get it within this epsilon. Maybe you saw this when we were going through Math 632 or the intro to grad level mathematics, wherever you were. You saw this definition. So this is how these two definitions coalesce. Notice, however, that the definition given up here is this is for X being any metric space. So we're going to be using this definition a good bit more because we're going to see this as being a more general framework that we can be working in. Let's start by looking at how this intuition holds for the real numbers. We've just shown that all points in A, B are interior points. But in the closed interval from A to B, all points other than A or B are the interior points. You cannot say that A or B are interior points because regardless of what epsilon you might choose, there's going to be some part of the epsilon set that's hanging out of the closed interval going from A to B. What points in the natural numbers are interior points? None of them. In fact, points in the natural numbers we will be calling isolated points. And that's going to be because if I consider for all epsilon greater than 0, if I consider the set x minus epsilon, x plus epsilon, and look at how its intersection works with just the set containing x, or rather just the set natural numbers, then that's just going to be x. This actually needs to say for there exists an epsilon greater than 0, because you can make your epsilon big, but this is saying for a sufficiently small epsilon, then you can find a point there such that x minus epsilon, x plus epsilon intersected with the natural numbers is equal to x. And we've talked about how you could play around with epsilon equals 1/2 in that respect. What points in the rational numbers are interior points? None. There are no points that are interior points. However, no point of the rational numbers has this property as we were given up here. Namely, no point of the rational numbers is isolated because anytime that you give a little epsilon window around a rational point, you get infinitely many other rational points. But no point in the rational numbers is an interior point because if you take a look at that epsilon set, you also are going to contain infinitely many irrational points. So you're never going to be able to get an open interval that merely contains of rational points. So these cannot be interior points. How about the discrete metric? Here's something that I want us to think about. Now we're getting into the realm of discrete metric here. Remember that this, in terms of the discrete metric, was we're looking to say, is it true that you can get a ball x of radius epsilon that says that this is completely inside of a set A? Where here A is a subset of the set X given the discrete metric. Can we find an epsilon greater than 0 so that this is completely contained within the set A? What points in A that we could be choosing from, X being an element in A, are interior points? All of them. Let epsilon equal to 1/2. And we once again see that the fact that there's this lack of continuity between the jump from 0 to 1 and the distance means that, kind of like with the natural numbers, you can find an epsilon value so that the ball at that point of radius epsilon is just that point. So of course, that's going to be a subset of the set A entirely, because this is just the set X when epsilon is equal to 1/2. So to be clear on that, let epsilon equal 1/2, then the ball around X of radius epsilon is equal to just the set X, which is, of course, a subset of A. As we started with saying this point was an A, to ask if it was an interior point. So something to kind of break our intuition there, especially since discrete metric is very good at that. It tells us, okay, well, maybe not all of the same properties that we were used to happen here with all these other metrics. Then we move on to talking about boundary points of a set E. You see any points X, this is not necessarily those points in E, is said to be a boundary point of E if for all epsilon greater than 0, that this intersection of the open ball of radius epsilon intersected with this set E, which takes out X, is not equal to the empty set. Essentially, we're saying that something is a boundary point if you can say, okay, well, it doesn't have that same sort of isolated nature that we saw from before. That is, no matter how small you make your little epsilon window, then even if you just take out the value of X, you can always find something else there that is inside of that little epsilon window. Think about how that works with the point 1 here in the collection of all sequence elements of 1 minus 1 over n. The number 1 is not in this set. Notably, there is no n value that makes it so that this is equal to 1. However, no matter how far you widen your neighborhood starting at 1, you can always find, in fact, infinitely many points of this sequence that is going to be inside of that epsilon window. So you will always have a point in that set. That means that 1 is a boundary point. What other boundary points are there for this set? In fact, the answer is none. You can go through and show that, in fact, every single other point inside the set is an isolated point, and that any other point that you might choose has some sort of little epsilon window that you could be forming around it. Think about where those points would have to be. They would have to be either too far right, too far left, or in a gap in which you could put a little open interval. Let's keep going through with this sort of processing and see a couple more examples. What are the boundary points of a comma b, the open interval? That's going to be the entire closed interval from a to b. This suggests a notion of something we'll talk about in a bit of closing a set. Including the boundary points from a comma b is going to give us a closed version of this interval. And we'll be more specific about what we mean by that in a bit. What are the boundary points of the rational numbers? All of the real numbers are boundary points, because even for irrational numbers, whenever you take in a little epsilon window around there, you're still going to be able to find a rational number inside of there. So even if this is square root of 2, you'll still be able to find a value that is close by that gets you to say, okay, well then no matter how small I make my epsilon, I can still find a rational number. So all of R, notice here that this means that, again, we see another example where the boundary points are more than just the elements of the set that we're talking about. It's in fact the entire set of irrational numbers as well. What are the boundary points of a subset A of a discrete space? There are none. And this might be something that's cool for you to go through and check. Leave this as a little bit of an exercise to show that there are no boundary points here. Try playing around with those epsilon values that we know are pretty good to look at when it comes to discrete spaces. What about this one? What about the boundary of all little L2 sequences such that the sum, as I goes from 1 to infinity, of the absolute value of x sub I squared is less than 1? Well, I should have written a less than or equal to here, so I'll go ahead and change that. This should be the set of all sequences x inside of little L2 such that this value is equal to 1. Let's talk a little bit about as to why. Remember that to say something is a boundary point inside of this would mean to say that any ball of radius epsilon that you might intersect with this point, with this set A that we're talking about here, if you take out whatever x that you're talking about, that this needs to be non-empty. So let's think about that. Well, what are the points that are going to be close to a value of x, then x here being one of our little L2 sequences? Remember that the notion of close with this is based on that D2 metric that we use for sequences, which is to say that we're taking the sum of I equals 1 to infinity of absolute value of x minus y, x sub I minus y sub I squared, and then taking that to be square rooted. We usually do this with the real numbers as well, but I'm going to go ahead and gauge closeness by looking at d sub 2 squared. This just allows me to not have to think about the square root right now. Don't want to really have to think about it anyway. It just kind of complicates matters. But I'll know that if I'm getting my d sub 2 values to be close, then my d sub 2 squares are going to be close, and vice versa. Maybe the epsilon values are different, but for example, if d sub 2 converges to 0 for x and y sequences, then d sub 2 squared would also converge to 0. So I don't think that there's much harm in here in making this work. By the way, I could say a similar thing about Cauchy sequences. We know that there's a distinction now, thanks to last week's material. So, what about it? How can I show that something that has sum as I goes from 1 to infinity, where x sub I squared is equal to 1, is close to anything where this is less than 1? Well, think about this. I'm going to be taking a ball. Let's say that this is an x such that this is true. Then I'm going to be taking the ball around that epsilon and looking at all of the things that are close to that point. Well, what is something that could be close to that point? Maybe I could take something like this. Maybe I could look at something where I'm saying, okay, I know that the sum of these x sub I squareds is equal to 1, but maybe what happens if I take some x sub I and I subtract it by something very, 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 very small? How small should I make it? What about epsilon over 2 to the I or something like this, right? So let's say that I have something like this. Let's take a look at this sequence before we continue. This epsilon over 2 to the I starts like epsilon over 2, epsilon over 2 squared, epsilon over 2 cubed. So if I look to see what happens here with this type of example, then what I'm looking at is something like this. I know, first of all, that the sum of these values, if I'm calling this maybe y sub I, as I goes from 1 to infinity, the absolute value of these y sub I squares is going to give me, well, something pretty wild. It's going to give me something like, I think it'll be like the sum of epsilon squared over 2 to the power of 2y as I goes from 1 to infinity. And I could say, okay, well, how can I figure out what the sum of each of these values is? Well, I have something like 1 over 4 plus 1 over 16 plus 1 over 64, and that's our geometric series. So we're looking at something that's like what? 1 over 4 times 1 minus 1 over 4. So this is what? 1/3? So I'm looking at something that is basically epsilon squared over 3 when I take a look at it. If I wanted this to have an epsilon in it, then I could have just replaced this with square root of epsilon on the inside here. And then I would have the square root of epsilon squared, and then this would have been epsilon over 3. Now I have something very, very small to be taking a look at. This is something very small, and when I consider subtracting this from x sub I, it's also going to be making a lot of these values smaller. Let's say, without loss of generality, that maybe I'm looking at x sub I values that are all greater than or equal to 0, so that I can remove these absolute values just for the sake that it makes our value a little bit or makes our argument a little bit easier. If I had some negative values for x sub I, I would maybe have to add these guys inside of this sum. But otherwise, I'm going to be taking a look at my value z, which is going to be x sub I minus some sort of minus these values of the sequence, x sub I minus y sub I. So something like the square root of x over 2 to the I. Well, if this is how I define my z sub I, then I am really, really close to my x sub I. Again, let's go ahead and assume that our x sub I is greater than or equal to 0, so that when I'm doing something like this, I'm not that far off from the value of x sub I here. Now, how close am I? Well, let's say that epsilon is small enough so that maybe this is still staying to be greater than 0, at least for sufficiently many z sub i's. Then I could start imagining that looking at an example like this, I start seeing that, okay, well, the sum of these z sub i's squared maybe is going to be a little bit less than 1. Maybe there's a bit of an inverse triangle inequality that we could use here, right? So something like maybe the fact that this is x sub I minus y sub I in terms of its sums when we go through and square these. So this is using that little bit of a triangle inequality there. So this is a little bit different than our triangle inequality. Usually we would have something like x sub I minus y sub I squared is greater than or equal to something like this. But if we looked at this in terms of the one norm, it would be the inverse triangle inequality, right? This is now the inverse triangle inequality as we saw it from before. The only issue is this little squared guy, but that's maybe not the focus of this particular lesson. If we saw x and L sub 1, for example, we would automatically know that this is good enough. Otherwise, we have to do a little bit more work. Maybe we just be a little bit more careful in how we define some of these values right here, like the square root of epsilon over 2 to the I. And once we're a bit more careful about that, we should still be able to get something that is close to this particular value. And so the fact that this is 1 minus epsilon over 3 tells me that, okay, I have something that is 1, but something slightly smaller than 1. So I should have something that has that intersects non-trivially with this set A that we're looking at. So what was the goal of all of that? It was to show that whenever I have something that where the sum of the x sub I quantities squared are equal to 1, that I should still be able to, at least our intuition is telling us that we can still get into that set A. This tells us that our intuition for this set is still pretty okay. We're still looking at the things that are on the inside here, and maybe at the start we're considering the dotted set to get all of these and asking what are the boundary points of this? We would expect the boundary here to be including these values right over here. And indeed, those do seem to be the boundary in terms of our geometric intuition, and it turns out they are also the boundary as they actually are 4 sequences x sub I. And we can kind of see this a little bit by just saying, let's take x sub I and just nudge down the values a little bit. Maybe there's a sequence along these lines that we could be using, although maybe my sequence that I've chosen is a bit too simplistic for the little L2 case. It probably would work pretty well for the little L1 case. Whew. So that kind of tells us a little bit about how we can be seeing stuff inside of these arbitrary sequences, that these points on the interior are still sequences, right? That they work the same sort of way. Our notion of metric spaces, right? How the geometry of these spaces works holds true for even spaces like little L2, and we can see that in an algebraic sense as well. Let's talk about those closed sets. Let's define a set in the real numbers. Again, this is what I tell my undergraduate senior students when we're going through advanced calculus, is that a set E is closed in the real numbers, provided that every boundary point of E belongs to the set E. And we can generalize this for the notion of when you have boundary points of an arbitrary set in a metric space. In that case, of course, you're just replacing E with X, or rather the real numbers with X. So you're saying let E be a subset of a metric space X. Then E is closed if the boundary points of E are contained in E. So we have some examples here in terms of the real numbers. The empty set is closed because the empty set has no boundary, so it is going to be closed. By the way, for the same reason, every set in the discrete metric is closed, because we've talked about how in a discrete metric, every subset of that discrete metric has no boundary. Hence, this definition is vacuously holds. Every boundary point, there are no boundary points, belong to E. And we would say that those sets are closed because the only thing that they had to do was say that if something is a boundary point of E, then it belongs to E. And that's true in the sense that there are no boundary points of E, so there's nothing to say that it's false. That's what we would maybe call like a vacuous statement. Doesn't really have much meaning to it, but we do go ahead and allow that here for this definition. So the empty set is closed. Every set in the discrete metric is closed. The open interval from A to B is not closed because A and B are boundary points, like we said, for this open interval. Whereas the closed interval going from A to B is closed. The set of natural numbers is closed because every point of the natural numbers is a boundary point, and there are no other boundary points. However, we said that the boundary points of the rational numbers include the irrational numbers, so the set of rational numbers cannot be closed. Something interesting that we can look at here is the closure of a set. This is what I was talking about before, of like you can consider like a kind of a closed set associated to an open set. And it comes from including the set of boundary points inside of the set E. Exactly how we're defining this E bar. We would say that the union of the set of all points inside of E together with its set of boundary points is the closure of E. Notice that we're including E inside of this set. Because remember, for example, if you just have the set containing 0, that 0 is not a boundary point of the set containing 0. Because if I delete 0 from the set, any open interval around 0 is not going to contain any elements of that set, because now that you've deleted 0, the set is empty. So we do need to include the set E whenever we consider the closure. This also guarantees that E is contained within the closure of its own set, that we're only adding in points, and that the points that we're adding in are going to be those that are the boundary points of that set E. And that's how we define to be the closure. So notice here that the closure of the open interval is the closed interval, that the closure of these closed sets happen to be themselves. And in fact, we'll say and show at some point in a homework exercise that the closure of a closed set is closed. In fact, it's itself. And then finally, that the closure of the rational numbers is the real numbers. Something that'll be useful to us in types of problems that live in this sort of topological realm are things that we're maybe familiar with. We've seen these things perhaps if we've gone any sort of direction with open and closed sets, but maybe we've only done these in the real numbers. The problems that we're going to be seeing here that deal with open and closed sets look something like this. Show that the closure of the union of two sets is the union of the closure of closures of those two sets. And this is something that we can do in a general context. We do not need the specifics of the real numbers to do it, which may be where we did these in a previous class. Here, however, we can just go through and use the notions of metric space, if that's even necessary. In fact, for this problem, we're not going to really use metrics very much. We're not going to use it in one of our directions. We will be using it in another one of our directions that we'll see in just a short while. But let's get some exercise here with what these sorts of problems look like. So let's start by showing that this E sub 1 union E sub 2 closure contains the closure of E sub 1 union with E sub 2's closure. Well, first we note that E sub 1 is contained within E sub 1 union E sub 2. Then I'm going to make this claim and ask for you to back it up. The closure of E sub 1 is contained within the closure of E sub 1 union E sub 2. I want you to think a little bit about why that's true. Think about boundary points and how these things relate. Think about how the sets themselves are contained within one another. So the real thing to think about here is to think, is there a relationship between the boundary of E1 and the boundary of E1 union E2? Is there some sort of relationship here that might be useful here to help me say that the E prime values in E1 are contained within the E1 union E2 prime values? I want you to kind of think about that, consider that using some of your set notation and get some practice with our metric balls there. Similarly, we could say the same thing if just E2 is inside of there. So by definition of set union, we get the inclusion that we were looking for. The other direction is going to be using some of our epsilons. So this is going to be a little bit different if you have seen things from a more geometric, or rather just a completely abstract topological perspective, is that now we get to use the fact that our sets E1 and E2 are contained within, are defined in a specific way in terms of boundary and so on and so forth. So let's see if we can do that. Let's let X be the inside of the closure of E1 union E2. Then by definition of closure, X is either in E1 union E2 or it is in the boundary, it is a boundary point of the union of the set. Well, if X is in E1 or E2, then it's inside of the closure of E1 union with the closure of E2 automatically. So we don't have to worry about those. So let's assume that X is a boundary point. If we claim that X is a boundary point of E1 or of E2, that means that X is going to be inside of the closure of one of those two sets, in which case we would also be done. So by way of contradiction, we need to say that X is going to be a boundary point of the set E1 union E2, but it is not a boundary point of E1 or of E2. If we do claim that, then we have the statement automatically. So we need to try and go through the opposite case, and we will try to go through it using contradiction. Well, there is going to be some epsilon 1 such that the ball around X of epsilon 1 is intersected with E sub 1 is only intersects at the point X. It does not intersect anywhere else. And similarly, we should get some sort of epsilon 2 so that it does not intersect with E2. Well, we're just going to take epsilon to be the minimum of those two values. And by a containment argument, we can just say that now the ball that is of radius epsilon cannot intersect at all E1 or E2 except at the point X, the center of this ball. Right. The picture that we're working with here is that you're saying because you're looking at the set of E1 union with E2, that because something is a boundary point of the closure, right, the closure of this set, so we're closing these guys in right here. If something is in the closure of this set, then you're looking at something that either is going to be E1 or E2. If you tried to pick up some other point that was not, then you basically would have to say that it's actually something that is its own isolated point. And if it's its own isolated point away from E1 and away from E2, well, then we end up figuring out that this cannot be a boundary point of E1 union E2. So that's kind of our picture of what we're looking at with this problem. So this is a lot of what our problems will look like when it comes to open closed sets, boundary and interior points, and the like. My recommendation is to use some of the problems that we're doing in the homework and start practicing with them a little bit, to making sure that you have good arguments with them. and working with them. If you haven't been working with other people in the class at this point, this is very much a good time to start doing so, as we're going to start approaching our arguments from multiple different perspectives. You've already seen how many perspectives we need for just what were introduced in the last week, how we introduce things in terms for continuity and for convergence and for things like this. And so now we're going to start approaching some of these arguments from a notion of open or closed. And when we start doing that, sometimes it's tricky to say, okay, well, what is the right approach that I need to be taking here? And a lot of that comes from intuition of working with these problems. Use your peers as a guide through this class. Work with other people to come to a conclusion like, this is actually okay, or I need to work on this a little bit more. And that is something that is usually best understood or found when you are working right alongside other people who are struggling at that same level that you're at. Let's see a little bit more about open and closed sets. Today, I just want to talk about these sets, especially when it comes to the context of metric spaces. If you're familiar with an abstract definition for topology, a lot of these are going to be very familiar propositions, but the proofs of these are going to maybe not going to follow the same sorts of lines as you're going to used to take. So my recommendation is to be studying those lines a little bit. Look to how those lines are. How are you using interior and boundary points to help define these sorts of propositions? Whereas if you have not had an abstract topological background, then a lot of these propositions are probably new. So my recommendation for you is twofold. Try to understand how the proposition is, right? What is it trying to say? Does it make sense to me? Is this something that I find could be useful in a particular context? And then finally, look through the proof to say, okay, I understand where these things are coming from. Maybe you've already started doing this with the exercises, but my recommendation is to try working the exercises that we go through yourself first here in the videos before you watch me do it. Now that you've seen me do it for 3 weeks, you get a general idea of what I'm looking for and what are the things that I find to be important. But for some of these examples, I want you to start trying to work through them before I start working through them and see how you would go through and approach this problem. That is going to be just as important to help you feel more edified as you come into the homework because you've already gotten practice. Let's take a look here at this proposition. Let's take a subset of a metric space. Then the following things are equivalent, meaning we could go from 1 to 2 or 2 to 1. If both one of the statements are true, the other is true. One of these statements is false, the other statement is false. This is a biconditional between these two statements. Then the first statement is F is closed, and the second statement is F contains the limits of every convergent sequence of elements inside of F. This second part, to break it down, is to say that if you have a convergent sequence that consists of elements inside of F, and it converges to a particular point X, then X is going to be inside of that set X as well. So if X sub n is a subset of F, and X sub n converges to X, then we're saying that this implies that X is also inside of F. So let's take a look at that. Let's start by saying that X sub n subset of F converges to A. Here we're using the fact that 1 is the antecedent of our conditional here, so we also know that F is closed. Well, then for epsilon greater than 0, the ball centered around A of radius epsilon contains infinitely many elements of X sub n. Well, that's going to mean that this is absolutely going to be a boundary point of F, since here epsilon is going to be arbitrary. But the boundary points of F are contained in F since F is closed. So A is going to be inside of F. So notice that our approach there was to claim that A was a boundary point because there were so many elements of F inside of any open ball around the point A. The sequence was a huge help, by the way. It's exactly the infinitely many elements that we needed. Let's go the opposite direction. But notice we're going to do it using the contrapositive. So we're going to start by saying if F is not closed, then there is some boundary point of F not in F. What we need to do now is show that there exists a convergent sequence consisting entirely of elements of F, such that it does not approach a value in F. In which case, this sequence in particular, we're going to say that this sequence attempts to approach this boundary point of F that is not inside of F. We're going to call that point A, and since A is a boundary point, there is some point X sub n within the ball centered at A of radius 1 over n. So the picture here is we've got our point A, which we're saying is not a boundary point of the set F, or rather, it is a boundary point of the set F, but is not inside of F. So if I'm looking at what this set F is, I have something that looks like this. Maybe this is my thing that's not inside, and maybe some of this stuff is inside, who knows? And I get some sort of set along these lines. But because it is a boundary point, if I contain any ball with this center on the inside, then I can still find a value to call an element of my sequence, which is going to go to an element inside of F. And as we'll see, this is a Cauchy sequence. This sequence x of n is going to be within the ball of radius 1 over n. And so no matter how you go through and make it work, in fact, this has to converge to A by our definition. It's Cauchy and it converges to A using the definition of convergence to A. So the sequence x of n, consisting entirely of elements of F, converges to a boundary point A, which is not inside of F. And that's exactly proving our statement by the contrapositive. Let's talk a little bit more about open sets, because we've been looking at open balls as the things to kind of to work with, but closed sets have this kind of sensation of an interior as what we've been looking at. We've already seen some of these things already, so I'll just go ahead and brush through them quickly. We've said that for real numbers, that everything is an open point, at every open point is here. I have not defined this set here, which this term here, which is the set of all Clopin sets on a metric of R, and this is exactly where that notion of connectedness comes in from before. So I can actually define X to be a connected set, and we'll say here that X is a metric space, to be a connected set if the only Clopin sets, that is, the sets that are both open and closed of X are the empty set and the set X. So this is the collection of all Clopin sets within a connected set. To give an example here, notice that the real numbers are connected as a result, and the geometric intuition that we get from real numbers is that there cannot be any separation. If you're looking at all of the possible ways that you could be working between any two given points here, then you're going to get something here that is connected here. Now, on the other hand, the set 0, 1 union with 2, 3, this set is not a connected set. This one is disconnected. And that's because you can actually make an open or a closed set on this set using the relative topology or the relative metric that this inherits from R. Namely, if you take the ball of 1/2 of radius 3/4, then with respect to this set, remember that the way that this ball is defined is you're going to take this ball and look at its intersection. So let's say that this is the ball in R of 1/2, 3/4. And we're going to take its intersection with the set 0, 1 union with 2, 3. Well, the way that that's going to be defined is this is just going to be the set 0, 1. Notice that this ball is an open ball centered at 1/2 of radius 3/4, but it does not contain all of the things that are outside of this set because this is our metric space with respect to this. It's just getting the relative metric on it. This is with the relative metric that it gets from R. On the other hand, even if I took the closed ball, so this is the closed ball of this space. Remember, this is going to be all of the values that are not only less than 3/4 when their measure is given or their distance is measured away from 1/2, but this is also those that equal 3/4 as well. But this is also equal to the set 0, 1. So notice that because of this, the 0, 1 is equal to not only an open set, which is, we've said the open balls are open sets for this space, but it's also equal to the closed set, BR. So this is 1/2, 3/4 for this closed ball. That means that this is a Clopin set. So because we found a Clopin set in this metric that is not either the empty set or the entire space, this is a disconnected space. And geometrically, that makes a lot of sense. You have, looking at this space, you've got 0, 1, 2, 3. You're looking at all of the values inside of here, as well as all of the values inside of here. There should be some sort of clear disconnection here between these two sets. All right. So that's kind of the new thing here, I think, and generally everything else that I've said is maybe clear. Maybe it's saying the sense that discrete topology, every set is open, is not something that I've mentioned. So maybe something neat to kind of take a look at here. And in general, we can now say for any set that you are given, even those that are neither open nor closed, you can take the interior of that set E. The interior, kind of like the closure, is going to be taking the set of all interior points of that set E. So for example, the interior of the open interval from A to B is just itself. The interior of the closed interval from A to B is the open interval from A to B. And the interior of the natural numbers or the rational numbers is the empty set, because neither of these sets has any interior. So the interior of a set we could make similar claims about, and maybe we can start connecting them with the notion of closed sets once we finish out talking about the connection between open and closed sets in a future slide. But for now, I want to focus on this notion of open sets, because this is something that I hear a good bit from my undergrad students, which is, what do the open sets look like? Because closed sets are actually harder to get a grasp of than open sets. And many of my students are quick to jump on when I say, okay, well, how would you characterize open sets? And they always say it's these. It's the open intervals going from A to B. But what about the interval, like say 0, 1, union with 2 and 3? Every point inside of either of these open intervals is an interior point, and so hence everything there is going to be an interior point. Notice that there exists a ball of radius epsilon that is completely contained within 0, 1 for any point that you might choose with it, because it does not have 0 or 1. And the same thing can be said about the open interval going from 2 to 3. In fact, we can characterize all open sets in the real numbers in the following way. There's going to exist a sub 1, b sub 1, a sub 2, b sub 2, so on and so forth, that says this is going to be this open interval. It is a countable list, in fact, of open intervals to make this work. Notice here, this a sub 1 could be finite or infinite. And then if this list is finite, say a sub 1 less than b sub 1 equals is less than a sub n is less than b sub n, or equals b sub n minus a sub n, something like this. Then we can say that this list, then b sub n can also be finite or infinite. I do have to make a quick change in my notes here, so I'll go ahead and do it, because it is very much possible that b sub 1 is not equal to a sub 2. Looking back up at our previous example, we see that, so this just needs to be a less than or equal to here. So any non-empty open set of real numbers can be written as a countable collection here of open intervals, right? So you can also have this be a finite list. It could end at a specific point, or it could be an infinite list, very much like this set right here. So all open intervals, or all open sets in the real numbers, are just countable unions of open sets. Here's a good exercise. Show any uncountable union of open intervals can be written as a countable collection, countable union of open intervals. Or equivalently, show the theorem, right? Essentially, we know that open intervals, you can union as many things as you would like, or you could just go through and show that this theorem is true, namely that you only need countably many things. How could you work with an uncountable union of open intervals if you were given it? How could you break it down to just countable unions? Okay, so let's take a look here at this problem. Let's show that the open ball around this epsilon is an open set, given our definition of open. Namely, we want to show any point in the ball centered at x of radius epsilon is an interior point. So let's see if we can do something like this. Here's our picture to kind of help us out because I wanted to give a kind of a geometric notion here. This is that same picture that we saw in the previous week. It has come back to say hello once again. Let's take a point y inside of this open ball. And you can kind of see what we want to do with this is that we want to try and find some value of delta that makes this work, right? We want to try and find a delta such that that particular ball on the inside fits entirely inside of the epsilon ball, even if this value of y is not equal to the center x that's given inside of here. Well, how are we going to do this? Then the distance between x and y is strictly less than epsilon. That's by definition of y being inside of here. We must have this distance as true. So let's think about how we could try and formulate this ball. Let's claim the following. Well, I know that I want to have this delta be somewhere so that the entire ball fits within epsilon. Here's that distance between x and y. So what's a good idea for what delta should be? Well, since this entire radius is epsilon, I think a good claim here would be to say that the ball centered around radius y of radius epsilon minus the distance between x and y should be completely inside of this ball. So that seems like it should be a good claim. Our picture certainly says that, but can we do that using the definitions of metric spaces? Note that if z is inside of the ball y minus dxy, then we want to show that the distance between x and z is less than epsilon. So let's see if we can do that. The distance between x and z is less than or equal to, by the triangle inequality, we're going to compare this to the value of y, plus the distance between y and z. Well, we know that this is equal to, or in fact less than, the distance between x and y, plus, because the distance between y and z, since z is inside of this ball, this is less than epsilon minus dxy. This is equal to epsilon. So, since the distance between x and z is less than epsilon, we must conclude that z is inside of the ball x epsilon. This is as desired. So we can just put a little done, put a little smiley face, end this out as however we would like. So this works very well. We just proved our claim and we are good to go. So any point inside of this is an interior point, which is the definition of an open set. And we've just gone through and shown that that works for this. Our picture intuition is indeed exactly right, and we can see where that comes from using the triangle inequality with this line. Let's finish out with a few more things. I don't have many more exercises for us to go through. I just want to talk a little bit about the relationships between open and closed sets here. Let's just take the complement of the set A, which we've been defining as the points not inside of A but are inside of our metric space. So here our universe is the metric space. I'm going to claim that A is open if and only if B is closed. That means if A is open, then the complement of that set is going to be closed, and vice versa. If A is closed, then B is open, however you would like to proceed it. Now, both ways we're going to go through and take a look at this in terms of a contradiction proof. Here's how it will work. We're going to say that A is open and assume B fails to be closed. Well, that means that there is some boundary point for B that is not inside of B. Let's take that point Z, whatever it is not going to be inside of B, so it has to be an A. Well, remember, A is an open set, right? So this means that Z is an interior point of A. So there's got to be some epsilon greater than 0 so that the ball of radius epsilon around that Z is continually within A. But that neighborhood cannot intersect B by our notion of complement, and that contradicts the fact that Z is a boundary point. Notice that this here, we're kind of using against each other the notions of interior and boundary point. In some sense, they're very much opposites of each other. If something's in an interior point, it's completely contained within for the set. If it's a boundary point, it cannot be completely contained within. It is going to contain some stuff that's within or without for that set. In fact, here, I wrote this with a set of real numbers in mind, but I was really thinking of let A be a subset of a metric space X. So here, this is also true for these spaces. So what does this mean? Let's take something like the discrete metric. If we take the discrete metric, remember that we've described that every set we've described that every point is let's say, so every set, which is the set X, is open. In fact, every set, the set X, is closed. We've said both of these things. We've said that every set, individual set, is open and it is closed. It's open because it is an interior point. We've done the epsilon equals 1/2 argument. We've said closed because the set X has no boundary. So every set there is open and closed. In fact, just from using these two things, we can now say, okay, well, every set X complement is going to be open, and every set X complement is going to be closed. And every set X complement is going to be open. That's a lot of open and closed sets already. Singleton sets are open, singleton sets are closed, and in fact, complements of those two things can be shown to be closed or open for these individual points. Going to the backwards direction here, if we now say, so here we've already done this part, saying that B is closed and assume A fails to be open, we're just going to go through and use that kind of notion of interior and boundary points and have them play against each other just a little bit more. And that will be for this latter half here of this proof. Here's another interesting theorem, which is that intersections of open sets are automatically open. This intersection may be empty, but the empty set is open, so we don't have any worries there. Otherwise, we're saying that if you take in your picture of open sets, bunch of open sets, if they have some intersection, then that intersection is open. Notice that this is that finite collection we were talking about there. Notice that the notion for union here is automatic for interior points, because if you're contained within one point, that's there. So that second condition we were talking about at the very beginning, that one that said, namely, let A sub alpha be an arbitrary collection of open sets, then the union over alpha of A sub alpha is open, comes straight from our definition. If something is an interior point of this union set, right, what we would need to be able to show is that these are inside of this set. But any interior point of this union, you could go through and say that there exists, that point is inside one of these A sub alpha. So there is some sort of epsilon ball that is contained within the A sub alpha, and hence it is contained within the entire union. And that would be a good enough argument for that. By a similar notion here, we're going to get a corollary that if A sub alpha, or rather I should be saying B sub alpha here, just to distinguish, is an arbitrary collection of closed sets, then the arbitrary intersection of closed sets is closed. So notice where this is coming from. This is saying that if you have closed sets, then the intersections is closed. Where is that corollary coming from? It's coming from exactly what we just proved. What we just proved is that when you take a complement of open sets, you get closed sets. Remember, we said complements of unions become intersections over here. So this corollary follows directly from that theorem together with something we talked about in set theory back in week 1. It turns out that we can do a similar thing here for intersections and for unions of open and closed sets respectively. I encourage you to take a look here at these proofs to see that we've now shown that these things have the 3 conditions of what we call a topology. And what's more, we can now go back to our example of what discrete spaces stuff we were looking at and see that not just every set X is open or closed, but that every set is open. And that's because every set is just the union of some sort of number of singleton sets. And you can always union however many sets that you would like there. As a corollary of that, since every set is the complement of some other set, every set is also closed. So the discrete metric is an example in which every single set that you could describe is a clopin set. The discrete space is a very disconnected space. Any set that you might put on the discrete metric for any given set is going to be very, very disconnected. Our pictures are telling us that they're just kind of everywhere. Every single point is everywhere, no matter how much circle you put around and what points you give there, that's a disconnection between that and all of the other points. So every set is open and every set is closed for the discrete metric, thanks to this theorem. Here is that other theorem here. I thought that I had just said that is like something else, but I've gone through and written a proof for that as well. Phew, good. I'm glad that you have this to take a look at later, as well as the corollary that comes from intersections of these sets being closed. Here's one last thing that I'll be asking you to do a little bit for work. This is the notion that I was saying that the closure of a set is a closed set, and in fact, the closure of a closed set is itself. Working through those parts of that lemma, I'll be asking you to do a little bit for work on your own in your own space. But those two parts together give us this lemma, which is another way to characterize a closure of a set. And we'll be using this from time to time. Let E be a set of real numbers, or even in this case, let it be a metric space, subset of a metric space. Then the closure of E is the smallest closed set containing the set E, i.e. if F is another closed set containing the set E, then the closure of E is contained within F. It is the smallest closed set. By definition of closure, E is inside of the closure of E, and the closure of E is closed. That's by our lemma over here. Let F be another closed set containing E, well then we're going to get the same sort of inclusion that we have from before. Remember, we did this in a previous step where we said that if a set is contained within another, then so are the closures. Hence, that means that because F is a closed set, that the closure of E is contained within the closure of F, which is equal to F. A very slick argument that is hiding a little bit behind it, but I've asked you to do some of the piecing together here for some of your homework. Then a corollary of this is let E be a subset of a metric space. Then the interior of the set E is the largest open set contained in E. It's the same sort of notion as closure of E being the smallest closed set, and then using this complement way of thinking through it. The way you think of the interior of a set is that it is the largest open set. That is, instead of containing E, it's contained within E. So there's a little bit of that dual nature between closure and interior here to be working with. But that does it for us today. We've talked a lot about these notions of open and closed sets. Hopefully you were using some of our intuition from real numbers when we talked about this during this. If not, I recommend trying to take a look through how do these concepts work in terms of the real numbers. Take off the parts where I crossed out a set of real numbers and leave those there and say, does that make sense to me in my head? Is that something that makes sense in how I would go through and think about that and use that as a connecting piece here? But these are also true in general for metric spaces now. We get to cross out real numbers and say something much more general for any set of metric spaces, where here we're using this notion of open ball and closed ball as our way to define these open sets, namely interior points are contained within the set that they are. So we've talked a good bit about this dual notion between open and closed sets, closure and interior, boundary points and interior points. So lots of different kind of dual natures going on here, going back and forth, and a couple of examples to try and help us out as well. We've also characterized all our open sets to be the countable collection of these open intervals here. But that'll do it for me today. Thank you so much. Have a wonderful day.